So the important term in 4.3 is what's called linear independence. And so what is here the ID? Again, I start with a similar thing which I just wrote down in the last section when I started talking about span. So if you have a vector u in R3, then u can be written as, so this is, you will see in a moment, exactly the same what I wrote down before. I just skip one step, so it's u1 times 1, 0, 0, plus u2 times 0, 1, 0, plus, oops, u3, sorry, I missed this, u3 times 0, 0, 1. And again, we can say this here is E1, that's here is E2, and that's here is E3. So it's U1, E1 plus U2, E2 plus U3, E3. And similar what I wrote just in the last section. And in the last section, we would say, oh, that means every vector in R3, in the 3 components, is in the span of E1, E2, E3. That means if you combine E1, E2, 3, you can make U, no matter which U someone gives you. So that was last section. This section, even it's not so obviously with our definitions, but the idea is that this way of combining U, not only it's possible, it's uniquely possible. So you cannot find other numbers here which make it, which here is obvious, no? Because if there's a 5 here, the 5 has to be here. How else can I make a 5 on top? No? If there's a 3 here, this has to be 3. There's no other way. And if there's a, let's say, a 7 here, U3 has to be 7. So the point is, this is unique. You can only make it in one way. And as I said, this will come up later in the next sections. So it's funny. So first they start saying, what does independence mean? And first they explain it in different ways. But in the next sections, not in this section, we will see, oh, this also implies the representation as a linear combination is unique. So the point about unique linear combinations is behind the word linear independence, or this is one of the things why linear independence is so important. Okay, but as I said, the first time they define it, it's kind of hidden, and it will come back in the next section. I just tell you already now. So the definition is a little bit different, but also explain a little bit better maybe the word why it's called linear independence. So we have V, a vector space, and again as a subset. So R vectors, which we put in the set S. And now the trouble with linear independence is a statement about something which cannot be done. I think that's one of the reasons why people have a harder time understanding the concept of linear independence. So then we say S, also this set with these R vectors is a set, not a subspace. It's a set. It's just really, for example, 2 vectors, no? Is linearly independent if, and now comes the problem, it's a negative statement, if no vector in S can be written as a linear combination of the other vectors, or of the better remaining vectors in S. And if a set is not linearly independent, we call it linearly dependent. Yeah, so linearly independent means no vector can be written as a combination of the others. Otherwise, it's called linearly dependent. So again, as an example, for example, if S has, for example, let's make 3 vectors. So if you cannot use V2 and V3 to write V1, and you cannot use V1 and V3 to write V2, and you cannot use V1 and V2 to write V3, then we call it linearly independent. So these two don't make this, these two don't make this, and these two don't make this. And now the thing is, don't make is kind of hard to say. And first it gets terrible, no? I mean, if you have a set with 5 vectors, you have to check 5 conditions. No? So this is kind of easy to understand. It means independent. So this doesn't depend on this doesn't depend on this, and this doesn't depend on this. So the definition is kind of clear in the sense, oh, that it means what it means to be independent. No? I don't rely on the other ones. No? Where we instead of when we say rely means they cannot make me. No? So they cannot combine these 2 vectors to make this vector. No? So instead of rely, you say linear combination. No? So that explains independence. Essentially, it means, maybe bring my pencils back. Independence means the directions are independent. With these 2, I cannot make this because in this plane, this is not contained. With these 2 in this plane, the blue one is not in. Also, I'm not sure how good my arrangement is here. With these 2, I cannot make this. And with these 2, I cannot make the red one. So these 3 vectors would be linear independent. When I make red inside the plane of blue and green, then they're dependent because with the green and the blue, I can make the red. Yeah. So linear dependence means one vector is in the linear combination of the others. Independence means, oh, we cannot make this and this turn it into this. Even we stretch and shrink each one and then add it. That doesn't help. So independence really is a good name for this. Also linear independence is a good name for the description, but our condition is kind of weird because we have to say, okay, this doesn't make this and this doesn't make this. So it's very hard to check for linear independence. So the first thing, as usual in mathematics, if there's something which is good to understand but difficult to check, we find an alternative description which is easier to check. And that is our first result now. And maybe I make this on a new paper so we have this and the proof together.